Hello, geometry students. This is going to be a long lesson because just like the introduction to triangles lesson where there were just a lot of terms related to triangles, this is an introduction to polygons lesson, and we have a lot of terms related to polygons. It's going to take 2 videos to get through all of the terms related to polygons. This one's going to be a little longer than the second one. And then the third one, we're going to practice using the terms. I don't think that one's going to be too bad either, but put together, these 3 videos are going to take a lot of time. So buckle up, get your notes ready, and let's get started learning about polygons. Now, in the previous lesson about triangles, we defined a polygon. What is a polygon? A polygon is a closed plane figure, so it's flat. It has sides that meet at angles. All of the sides actually meet at angles. And it's formed by 3 or more segments. We learned that the polygon that's formed by 3 segments is the smallest one, called a triangle. And in this lesson, we're going to learn that there's many more that we have named that are common for us to see in geometry. Here's a picture of some polygons. Notice that these are flat figures that all of the sides meet in angles. These are not polygons for various reasons. First of all, this first one is not made by segments, it's made by curves. The second one has a segment, but then it has a curve. It's not made entirely of segments, so it's not a polygon. The third one is an open figure. It's not a closed figure, so not all of the sides meet in angles. There's a gap. And then the last one is 3-dimensional. It's not flat, so that's not a polygon either. All right, so what is a side of a polygon? The sides are the segments that form. Let me change my poor language here. The segments that form a polygon are called sides. Okay, so they're line segments. They have a beginning point and an end point. Any segments that make a polygon are known as its sides. The vertices of a polygon, or the vertex, if we're talking about just one of them, is the point of intersection between 2 sides of a polygon. A polygon will have as many vertices as it has sides. So here I have a 1, 2, 3, 4, 5, 6-sided polygon known as a hexagon. How many vertices do I have? 1, 2, 3, 4, 5, 6. It's really helpful actually if you can to just mark the side or the angle you start counting at, just so you're sure you don't double count it when you go all the way around. Because these are closed figures, so you always end back where you started. All right, now let's take a look at some specific examples of polygons here. Now notice that we use these line markers and angle markers to show where we have congruent sides. So these little tick marks on the side show where there's congruent sides. And these angle markers show where there's congruent angles. If they were different sized congruent angles, some angle markers would have just 1 arc and some would have 2 arcs. And the 2 arc ones would show that they're congruent with other 2 arc angles. Okay, now we have special names for different kinds of polygons, depending on, we're going to classify them by whether they're sides or they're angles, or both are congruent. First of all, an equiangular polygon is one that has angles that are all congruent. Notice that letter A, all of the angles around the outside are congruent. The same is true of letter B. Now, when I define the next one, you're going to say, wait a second, is that the same thing as equiangular? If a polygon is equiangular, isn't it also equilateral? We'll talk about that in a second. An equilateral polygon is one that has side lengths that are all the same. So the sides are all congruent. So notice that all of these sides are marked with a tick mark, but then I can squish my polygon down and still have equilateral sides, and that's what happens here in letter C. It's still a hexagon just like letter A, but it's squished down. These sides are all still the same length, but it doesn't have equal angles. Now, you're probably wondering, what about B? It's equiangular. Doesn't it also have to be equilateral? And the answer is, for a triangle, yes. Any equiangular triangle is automatically equilateral. But for any other polygon, maybe some are, but these ones are not. I'm wondering if actually we might find that polygons that have an odd number of faces, if they're equal angular, they have to be equilateral. I'm thinking that's going to be true. But if I look at this hexagon, think about this. What if I took these two sides and lengthened them the same amount? So I stretched out this hexagon so it was longer along these two sides. It would still be equiangular as long as I stretch these two segments the same amount, but it would have a longer segment here. And I believe that's what's happening here. This segment and this segment are probably a little longer than the other segments. And if that's the case, it's not equilateral. There's no evidence here to show me that this hexagon is equilateral, but there is evidence to show me that it's equiangular. Hey, by the way, the easiest equiangular but not equilateral polygon for me to share with you is a rectangle like this up here. All four sides are 90 degrees equiangular, but it's clearly not equilateral because the top and the bottom sides are elongated. And I think that can happen with any polygon that has an even number of sides. You can elongate two opposite sides. It doesn't work I believe that all odd numbers, polygons with an odd number of sides, if they are equiangular, then they have to be equilateral, just like a triangle. All right, now we talked about this before with triangles. A regular polygon is a polygon that has enough fiber in its diet. It's a polygon that is both equiangular and equilateral. Letter A is the one that's provably a regular polygon. And then there's such a thing as an irregular polygon. An irregular polygon is a polygon that pretty much eats only meat and dairy products. It's a polygon that is not both equiangular or equilateral. So B, C, and D would be irregular. Even though C is equilateral and B is equiangular, it's still irregular because they're not both equiangular and equilateral. All right, let's talk about just a few more terms here. The diagonal of a polygon is a segment that connects two non-consecutive vertices. If we're connecting consecutive vertices, it's a side. What if we're connecting non-consecutive vertices? Well, here we have a picture of these blue diagonals. So this is my pentagon. There are 5 sides. If I connect side AC, the vertices AC, they're non-consecutive vertices. That's a diagonal that connects those two. Hey, how many diagonals can I draw in this polygon? Well, I can't draw a diagonal along a side, so I can't do AB or AE, but I could do AD and AC. We're going to see that there's a pattern to the number of diagonals that you can draw in a polygon later on. A convex polygon is one where all of the diagonals lie within the polygon. That would be like this polygon. No matter what, if I draw diagonals, none of the diagonals are going to stray to the outside of the polygon. A concave polygon is one that does have at least one diagonal that crosses outside the polygon. So it's going to have one of its angles is going to sort of protrude into the interior, or maybe intrude into the interior of the polygon. And it's not really in the interior of the polygon because interior of the polygon means within the sides. Still, the sides are excluding this little bit out here. But notice that we have this little cave kind of into the meat of the polygon over here. I'm choosing some strange words to describe this. The best words to describe concave and convex, therefore, are the words that are right here. At least one diagonal crosses outside. Look, if I draw a diagonal from this vertex here to this non-consecutive vertex right down here, look what happens. It goes outside the polygon for a little bit. And because it strays outside the polygon, that means that this is going to be a concave polygon. All right, and then just lastly, congruent polygons have to be exactly the same size and shape. All sides have to be congruent with another side on the other polygon. And not just a side, consecutive sides have to be congruent with the consecutive sides on the other polygon. That's what it means to have the same shape and the same size as well. So that means that all of the corresponding sides are the same length. All right, that is our first video. Lots of terms here. We're going to get some chances to practice these terms, especially in the problem set at the end of the lesson. But for now, we're going to move on to video 2, where we name some polygons based on the number of sides. We're also going to introduce a couple other new terms in that lesson as well. So stay tuned.